Hi, it's Kristen Atchison, and this is a continuation of our discussion of two-factor ANOVAs. We're going to be discussing effect size and APA style of reporting findings. So for the two-factor ANOVA's effect size, we're still using eta squared. It's still the same thing that it's been previously in all of our other types of ANOVA, that percentage of variability not explained by other factors. And we're going to, just as you would hopefully suspect, we're going to have a different effect size for each of our f-tests. So we'll have an eta squared for factor A, an eta squared for factor B, and an eta squared for the interaction. And just like it sounds like, it's the percentage of variability not explained by other factors. So if you look at the formulas, essentially we're subtracting out all those other factors to kind of look at that. So for A, we're going to take total and subtract B in interaction. For B, we're going to take total and subtract A in interaction. And for the interaction, we're going to take total and subtract A and B. So again, it's the same process that we've been doing previously for eta squared. And again, notice that numerator is also matches the eta squared. So we're eta squared for A, sums of squared A. Eta squared for B, sums of squared B. Eta squared for the interaction and sums of squared interaction. So again, it's going to be important that we're just matching those things up. I really feel that some of one of the most difficult parts of the two-factor ANOVA is just keeping everything straight. So if you really are good at the matching games from elementary school and preschool, I think we'll do well. It really is a factor of matching these things up because everything else is the same kinds of procedures that we've been doing with one-way ANOVAs and again with the repeated measures ANOVA. So how we report this in the literature, we're still going to have those descriptive statistics like we have with t-test and every other form of ANOVA where we have the mean and the standard deviation. Sometimes this is in a table or a graph, especially in these factorial designs because they're a lot more complex. Again, another benefit of having a graph, to report it with a graph, is you can see those interactions. And your audience is really like that. The audience who's looking at this is going to appreciate that. They can see that interaction better. So that's very beneficial. And then you can also see those main effects. So the complexity really lends itself to these graphs. Again, we're going to report the hypothesis test for all three terms. We've got 3 hypothesis tests. We're going to want to report all 3 of those hypothesis tests that we've conducted. So for each, we're going to include the F value, the degrees of freedom, the P value, and the eta squared. Again, remember that P value sometimes is non-significant. So it's not always less than 0.05. Sometimes it's greater than 0.05 if we weren't able to reject the null. So really remember that. With the other alternative, if you get your less than and greater than confused, you can always put n.s or non-significant for F values that aren't significant. So an example of what that would look like, it looks just like an F statement we've had previously. The only difference is that this would be, say, the F statement for factor A, and we would have another F statement for factor B, and another F statement for the interaction. So the only change here to the APA style is that, again, there's more of them. We only had 1 in repeated measures and one-way ANOVAs. Here we're going to have 3 again. When we're discussing our results in APA style, what's important is, again, to focus on that overall pattern of results. You've got to pay particular attention to those interactions, and you need to really talk about those in detail, like we've discussed in the factorial design part of the class. You're going to want to talk about basically each mean and talk about what is happening in each cell and how that's different. Again, we usually see a but or however or an except, those sorts of things, some sort of caveat statement in those interactions. To be able to really get good at this, you have to have a lot of practice. But you are getting practice in this class. So keep practicing those interactions statements. For a two-factor ANOVA, we have the same sort of assumption we've had previously. So so that each sample is independent of each other. The populations, again, must be normally distributed. And this is, again, all coming off of, this is all out of probability. So all this inferential statistics is coming off of that normal curve, the probability sampling off of this normal curve. So again, we need to have our samples come from normal populations. And again, we want them to have homogeneity of variance. We again want them to have equal variances. We don't want them to have big chain differences between them to begin with, because then we're not going to be able to, again, look and see if there's a treatment effect. So for our learning check, if a two-factor analysis produces a statistically significant interaction, then you can conclude that A, either the main effect of A or the main effect of B is also significant. B, neither the main effect of A nor the main effect of B is significant. C, both A and B are significant. Or D, the significance of main effects is not related to the significance of the interaction. Please pause it, think it over, go to your textbook if you'd like, kind of look up the answer, figure it out for yourself, and then resume the video. The answer is D. The significance of the main effects is not related to the significance of the interaction. Again, it's really important to remember that each F-test is independent. So if you find a significant on one of them, it has no bearing on the other two. So again, each F-test that we're going to be conducting is independent of each other. Here's another learning check. Decide which ones are true and false. Again, pause the video, work through these, and come back and listen to the answers. True or false, two separate single-factor ANOVAs provide exactly the same information that is obtained from a two-factor analysis of variance. And the second question is, true or false, a disadvantage of combining two factors in an experiment is you cannot determine how either a factor would affect participants scored if it were examined in an experiment by itself. Again, pause the video, go listen, work through the truth or falseness of these statements, and come back. Both of these are false. Main effects in two factors ANOVA are identical to the results of two one-way ANOVAs. But what's different is that two-factor ANOVAs also have interactions. Remember, that's that new thing that we get for factorial design. We can look at them independently, but we can also look at them together, that interaction. And the second one is also false. Again, two-factor ANOVAs allows you to determine the effect of one, controlling for the effect of the other. So both of those were false. Please review these slides, review the text, and please also go through that module on two-factor ANOVAs as well, so that when we come to class for practice problems on Wednesday, that we really can work through these things well.